Thank you.
Thank you, Arnab. Arnab is another person who, with a background in TIFR, is also working to make maths and science accessible to everybody. So I feel that we are in good company here with a lot of people who are working in that direction, and Arnab is certainly one of the most active persons. I would like to thank Junoon for providing this opportunity for talking about this subject, which is something that I have felt strongly about for many, many years. And I would like to begin by paying tribute to our guru in this effort. Is a person called Professor W. Sawyer. I don't know how many of you have heard about him, but he is one of the most profound teachers of mathematics, who has written on a variety of subjects, and he has been an inspiration to the work that I will be talking about. Next slide, please. I will ask a question here, but I probably will get an answer which is different from when I speak to most audiences, because the question was, how many of you dislike mathematics? Now, I don't expect very many people who dislike mathematics to make it all the way from, through traffic in Mumbai and come to South Mumbai. So anyway, let me ask it. And how many of you like mathematics? So all those who like mathematics, put up your hand. Yeah, this is a good crowd. Normally, this is not a very typical crowd. Yeah. If I ask this question in a normal school, then the answer is, when you ask how many of you don't like mathematics, a number of hands go up. The second question is, how many of you are comfortable in speaking the mother tongue in which you were brought up? I guess everybody here. Your mother tongues are different, but each one of us here is very comfortable in the mother tongue. And in fact, learning a language is not very easy. But all of us pick up the mother tongue without any special efforts. And among the children that I was working with when I first started trade union work, those children were familiar not only in their mother tongue, but they are from Mumbai. So if their mother tongue was Tamil, they were familiar with, quite comfortable in Marathi, in Hindi, in Tamil, their mother tongue. And I was always intrigued by the fact that how is it that children can pick up 3 languages, because I had difficulty learning languages myself. And why is it that these same children have difficulty in mathematics when they go to school? Next slide. Now, Sawyer was one of the first persons to talk about everybody learning math. He called it math universalization. And I want to highlight the last sentence. Such a change will seem fantastic to many people. So would universal literacy have seemed absurd a few centuries ago. To enter a new stage of history is always difficult, but he thought about everybody becoming comfortable with mathematics, and that was something that he wrote in 1962. Next. He says in that same article, the population today divides sharply into those who hate and fear mathematics and a minority of mathematicians. The remarkable thing is that such an outcome is accepted as normal. We accept this as normal. It is as if physical education cripples 90% of the children taking it. By the time children go through school and they reach class 9 and 10, I think it's a pretty good, pretty accurate statement to say that roughly 80% of those students don't like mathematics, no matter how good the school is. Even among the best schools, when you reach class 10, you will find most of the children disliking mathematics. Okay? And if you start at class 1 and class 2, that's not the case. So what happens between class 1 and class 2 and class 10? Okay, around class 5, more and more children start disliking mathematics, and when they reach class 10, they're very happy to, get past mathematics. So what is happening in school that changes this whole perception of mathematics from something which is not, too bad to something which is to be avoided? Okay. Now, let me give a test here to all of you to decide whether or not you will be able to like mathematics or dislike mathematics. Okay, this is a test which is a pretty good test. Now, here I have in my hand how many? Two stones, and here I have three. Okay, so there are 2 in this hand and 3 in this hand. And now, how many do I have in this hand?
5.
Okay, so all of you who have arrived at the answer of the participants in the front, all of you have passed the test. Okay, and now let's take this one step further. Okay, I want to write this now. What have I done? Mathematically, what have I done?
Subtracted 2 from 5.
I have subtracted 2 from 5, yes, but I've also, to begin with, I added, right? So, can you write down what I just did? What I just did, yeah, this problem which I just solved, can you write it down? Right, and can you write down what he said? That's another way of writing down, okay, what I just did. Okay, now let's look at this one here. And how much is this? How many of them is this? 5. Okay. Now, yeah, I'll hold it up also. So there were 5, okay. And now, how much is this?
1, 2.
2, okay. So how much is this? 3. How did we get 3?
By subtracting 2 from 5.
By subtracting 2 from 5. That's the second thing there. 5 minus 2 is equal to 3, right? There's another way of writing this. Okay, I could also write this in the form of, yeah, you wait here, you'll help me plot, okay? I can write this also as x plus 2, is equal to, we'll have to just erase that, 5. Because you don't know what's in this hand, so let me call this as x, right? We know what's in this hand, 2. And we know that what we had initially was 5, so we could write this as x plus 2 is equal to 5. Okay? Now, I'm going to do another problem. How many of them are here?
9.
Count properly.
9. 1, 2, 3, 4, 5, 6, 7, 8.
There's one here.
Yeah.
Just count it again very accurately.
1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8.
And there's one here in the center. Okay. Okay, so there's 4 here and 4 here and 1. So that's 4 plus 4 is 8 and 1, 9. Okay, so there are 9 of these counters which are here. Now, how many do I have in this hand? You don't know. Okay, so it's X. All right. And now, I've taken some more in this hand. How many do I have in this hand? This is X. Is this X? It may or may not be. It's a different number. So what is this? Y. Let's call this Y. Okay? All right? I have not taken anything from there, okay? So this is X and this is Y. Now, I'm going to ask you to come up. Please come up. Please come up here. And this is how many I have in my hand, okay? Don't tell me, don't tell them, okay? Take as many as I have here, no, from there. As many. Okay? Just hold it, close it, okay? Come here. All right, so he has in his right hand, just hold your right hand up, the same number of stones as I have in my right hand. Okay? How many were there initially? 9. Everybody remember? There were 9 in there. I've got X here and I've got Y here. How much does he have in his hand? Y. Okay? Now I'm going to put what he has in his hand and what I have in my hand down here. Okay? Put it here. Take it out. How much is this? 6. Okay? How much of this is? It's 6. And what's left here? 1. Okay? So can anybody figure out what I have in this hand?
2.
Ooh. Very good. How did you do it? Okay, but you figured it out. Very good, right. Okay. Now let's write down, thank you. Let's write down the steps, okay? The first step was, I took so many, right? So how many did I have in my hand? This is X, and this is? X plus Y. Please write that. That was how much I had in my hand. Then he came up and he took up the same, right? So, write what he took up. No, right? Okay. No, I didn't join those, so it's no plus. Just what he took up was just there. Write it in the second line. Yeah? So that's what he took up. And then we put it together. And what put together became how much? 6. So, is equal to? Okay. Well, I'm not going to bore you with the next part. Thank you. I'm not going to bore you with the next part of the calculation. But the moment you get to X and Y, it's no longer as simple as what was going on in their minds, right? But what was going on in their minds was just that. And what is that? That is solution of an equation with 2 unknowns, which is known as the simultaneous equations. Okay. So everybody here sitting in the front had solved a simultaneous equation. The moment we start writing x's and y's, it becomes very complicated or quite complicated. Okay. But it's the same problem. okay, this is the same as this is the same as this. So one question that all of you who don't like maths will certainly have is, why the hell do we have to get into x and y's? Why not just use our own common sense and think, if it's working so well, why do we need x's and y's? I'll just ask the question and leave it at that. Thank you. Yeah. Okay, let's continue. So with this experiment, or with this experience, we can arrive at some conclusions. The first conclusion is that the problem is not with mathematics. Okay. Second conclusion is that the problem is not with us. Okay. And if people don't like mathematics, then probably the problem is with the way we are learning mathematics. Probably the problem is with math education. Okay? And that's something that Sawyer constantly talked about. Let's see what he has to say about math education. Next slide, please. He says, the depressing thing about arithmetic badly taught is that it destroys a child's intellect and to some extent his integrity. Sawyer was writing back in the 60s, so he's using a lot of gender, inappropriate language, but I've left it as it is because it is his language. So please bear with that. His integrity. Before they are taught arithmetic, children will not give their assent to utter nonsense. Afterwards they will. Instead of looking at things and thinking about them, they make wild guesses in the hope of pleasing the teacher or the examiner. I think all of you who have taught math have experienced this, right? When you ask a question. Okay, next. He talks about imitation mathematics. Okay? He says, nearly every subject has a shadow or imitation. It would, I suppose, be quite possible to teach a deaf and dumb child to play the piano. When it played a wrong note, it would see the frown of its teacher and try again. But it would obviously have no idea of what it was doing or why anyone should devote hours to such an extraordinary exercise. It would have learned an imitation of music, and it would fear the piano exactly as most students fear what is supposed to be mathematics. Okay, next. And then he talks about rote learning. He says, in discovering something for ourselves, we have a sense of freedom and conquest. In memorizing something that another person tells us and that we do not understand, we are slaves. Okay? Now in this talk which I'm doing today, I would like to take you through every concept or deal with every concept in the sense of discovery. But there is a problem. The problem is that discovery does not take place on a time schedule. Okay? And I have to finish this talk in a time schedule. So I cannot take you through every concept through discovery. So at the beginning, I apologize. I don't expect everybody here to understand everything entirely, which could be the case if we had a lot of time, because then we could discover everything, and when you discover it, you've understood it. But I do expect, and I hope that in this talk, everything that I talk about will at least be plausible, in the sense that you would feel that, yes, if I had enough time, I would be able to understand this. That's all that I can achieve in a given time frame, because I want to talk about quite a few things. Okay? Next. So now, having talked about what kind of math we don't want to learn, here he identifies 3 criteria, Sawyer's, about what should be there in a good math course. And the first is that it should be enjoyable and generate steadily increasing enthusiasm in the pupils. Second, it should develop independence and activity of mind, curiosity, observation, and confidence. And the third is, it should make pupils familiar with the basic ideas and processes of math. 1, 2, 3. 1 is enjoyment. 2 is thinking, independent thinking. Only 3 is procedures, understanding procedures. Okay, in that order. Next. Now, he also talks about who is a mathematician. And it's very interesting. He says, the essential quality for a mathematician is the habit of thinking things out for oneself. That habit is usually acquired in childhood. It is hard to acquire it later. So, all of you who are here, if you like thinking things for yourself, then you are basically a mathematician. Okay? That is the most important quality of a mathematician, that you like thinking things out for yourself. You don't take things for granted. Don't take things just because they are told to you. Okay? You question those. You try to arrive at your own understanding of things. Okay? Next. And what is the most important thing for math education? He says the most important thing in the early teaching of mathematics is that the student should form the habit of weighing evidence, of deciding for himself. Okay, so this habit of individual decision of thinking for oneself, that is something that we focus on in early childhood education. And since he was talking about, remember in the first slide, he was talking about everybody learning mathematics, everybody being comfortable with mathematics. He also defines success in mathematics. And how does he define success in mathematics? He says, complete success would mean that every individual felt, I enjoyed the mathematics that I had time to learn. If I ever need or want to learn some more, I shall not be afraid to do so. So the definition of success is in terms of the confidence that the student has in his or her ability to learn what she is interested in learning. If you're not interested in maths, there's no reason to waste your time learning mathematics. But should you want to learn mathematics, then you should not be afraid to do so at whatever level you are. Okay, next. And then he talks about also how to learn math. He says, talks about geometry, but this applies to all branches of mathematics. The best way to learn geometry is to follow the road which the human race originally followed. Do things, make things, notice things, arrange things, and only then reason about things. Let's do a few examples of this, okay, to illustrate this point. Now, how many cubes is this? 2. How many is this? 1. So what is this? 3. And if I look at the colors, how would I say this? What have I done? I have joined them, you've added them, right? So what is this addition? Which numbers have I added? 2 plus 1 is equal to 3, right? This is what I've done. Now, let's do multiplication. We know that multiplication is adding the same number to itself repeatedly. So, what number is this? 4. What is this?
8.
As a sum, how will I say it? 4 into 2 or 4 plus 4, right? And what is this? 12, right? Which is 4 added to itself how many times? 3 times, okay. Now, but instead of joining like this, I could also join like this, right? So how much is this? 12. What is this shape? Rectangle. So if I take a number and I join it to itself repeatedly like this, what shape will I get? Rectangle. So multiplication gives us rectangles, and in every rectangle there probably is a multiplication represented. Okay, that is something that we have just seen. Okay. Now let's take. We know what are even numbers, right? Even numbers are those numbers which have 2 as a factor, right? Which have 2 as a factor. So can you tell me, is this an even number?
Yes.
Yes? Okay, is this an even number?
Yes.
Yes? Both of these are even numbers. Is this an even number? No. So what are numbers which are not even? What are they called? Odd numbers. So this is an odd number. And is this what kind of a number is this? Odd number. So if I take an odd number and an odd number and I add them to each other, you'll always get an even number. Right? And if I take an even number and I add it to an odd number, it will always be an odd number. And of course, if I take an even number and I add it to an even number, it will always be an even number. Okay? Let's look at the now square numbers are numbers which are when I multiply a number by itself. So this is 2 into 2, right? Which is this one here?
3 into 3.
This is 3 into 3. Which is this one here? 4 into 4, right? What is its shape? Square numbers. So when I multiply a number by itself, I always get a shape which is a square, which is why we call them square numbers, right? Now there's an interesting thing about these numbers that we know about even numbers, we know about the odd numbers, we know about square numbers. Let's just do a problem here now, where I write the odd numbers. Okay, which are the odd numbers? 1, 3, 5, 7, and so on. Okay? Now let me add them. If I add 1 and 3, what do I get?
4.
Now let me add the first 3 numbers.
9.
Let me add all these.
16.
But what are these numbers?
Square numbers.
Square numbers. Okay? So the question is, why is it that when we add the odd numbers in sequence, why do we get square numbers? Okay? Now it's a very interesting thing to discover why we get square numbers when we add odd numbers. But let me just take you through very quickly through how that happens. Okay? What kind of a number is this? Odd. Right? By looking at it, you can say it's an odd number. I can break this odd number into 2 parts. And put the even part, one part here, the other part here. And what shape do I get? An L. And the arms of the L are? They're not even numbers. This is 5, this is also, the arms of the L are, in length, they are equal. Okay, so every odd number I can make in this shape. Okay, so now let's look at the odd numbers. This is the first odd number, 1. This is the second odd number, made in that shape, right? And now I join them. What shape do I get? Square. Which is the next odd number? 1, 3, and 5. So this is that number 5. I join it. What shape do I get? A square. Okay. Which is the next odd number? 7. Let me take 7. And if we join it up, we get a square. And when we put the next layer, again we will get a square, and the next layer, again we will get a square. So now do we understand why the odd numbers added in sequence give us squares? Okay, right. And now we talked about square numbers, but there's also when I multiply a number by itself 3 times, that is 2 into 2 into 2, that we call it as 2 cubed, right? So this is 2 into 2 once, and I take this again 2 times. So I get this number here, which is a, what shape is it?
Square. A cube.
A cube, right? So how much is this? How many of them here?
8.
8. 2 into 2 into 2, right? So 8 is 2 cubed. And what shape is it?
Square. Cube.
It's a cube, okay? And now, which is the next cube number? 3 cubed, which is?
27.
27. Okay, let's see what happens. This is 3 cubed, which is also cubic in shape. Okay, so as you can see, there's a very close relationship between the numbers and shapes. But shapes you can make, right? Shapes you can make. Shapes are things that you make. So you can actually make numbers, you can join numbers, and most of mathematics is actually constructed by making something and joining it to something else and seeing what happens. Okay? This is something which, some examples which we have just discussed. Let's take the same examples and look at it slightly differently. The things that we have made, let's take those same things but look at it slightly differently. What is this? 2. What is this? 1. Okay, I'll again request you to come to the board and write down what it is that I have done. Okay, so you can erase that. Erase that. Erase it all. So what should she write there?
2 plus 1
Is equal to? Okay. Right? That's what she's written. That's what I've done. But this is 2 plus 1 if, there's an if. This is 2 plus 1, this is 1 and 2, if this is 1. Only if this is 1, then this is 1 and this is 2. But supposing now this is not 1. Supposing now this is my 1. Okay? Supposing now this is my 1. If this is 1, now what is this?
2. Here.
So now this is no longer 2. This is my 1. So this is 1 by 2. Okay? And what is this now? 1 by 4. Okay? So now this is my 1. I keep it here. This is 1 by 2. And this is 1 by 4. Now I'm going to join these. So what is this? 3 by 4. Okay. But what have I joined?
Half and 1/4.
Is equal to? So can you write down what I've just done?
Half plus 1/4.
Right. Okay. So it's the same thing, but now we are talking about addition of fractions. But if we know how to add numbers and we know how to join things, and then we know how to read what we've made, what we joined, once you know how to read that, you've understood addition of fractions. I'm not going to go through that, but addition of fractions is no different from addition of our normal counting numbers. Okay, thank you. Let's go to the next slide. That's what we just did. Okay, next slide. Now let's take some more examples. Supposing this is A. Okay, and this is B. So what is this?
A plus B.
Now it is A plus B. Okay. So this is A. I keep it here. That's A. Can you tell me what is this now? A squared.
Yeah.
Right? It's square that I've made with A. This is A squared. Right? This is A.
Some people are saying 2A.
Could be 2A also. Yes. Because A is 2 in this case. But if it's in general not 2, okay, it's 2A because here I've taken A as 2. Now let's think a little bit of abstractly. Okay. Let me make a square with what I've taken. So this was B, right? What is this? B taken B times. So B squared, okay? It's not 2B. A squared was 2A, but now this B squared is not 2B. Okay, it is 3B because B is now 3. Okay, so this is B squared and this is A squared. Okay, because now this is no longer 2, it's no longer half, now it is A and B. Okay, so this is A squared and B squared. And what is this now?
2B.
No more 2s and 3s. What is this? A. One side is A. Okay. This is B. The other side is B. Okay. A times B. Right. So now this thing is no longer 2 times 3. Okay. This is A into B. And I can actually join, this is A squared, B squared, and two of these, that means 2AB. What shape do I get? A square. If it's a square, it's a square of something. What is it the square of? It's a square of this number. It's a square of this number. So this is A and this is B. So this is A and A plus B here, A plus B here. So this is A plus B into A plus B, which is B squared plus AB plus AB plus A squared all joined together. So it's A squared plus 2AB plus B squared. Okay. And I can even take it further. Now I can go to cubes. Okay. So this is A cubed and this is B cubed. And this is B squared A and A squared B. Okay. And I can put them all together. So just look at what's happening here. B cubed plus B squared A, 2B squared A, 3B squared A plus A squared B plus 2A squared B plus 3A squared B plus A cubed. And what I get is a cube. Okay, the cube is A plus B into A plus B into A plus B. So it is A plus B the whole cubed, which has got 8 pieces. One piece is B cubed, the other piece is A cubed. There are 3 pieces of A squared B and 3 pieces of AB squared. Okay. Now we are doing class 7, class 8, but we're using the same things which we used in class 1 and 2. Okay. The point is that hardware and the software is both important. Okay, this is the hardware, but on the same hardware, you can put different kinds of software. This hardware is helpful in class 1 and 2, or even preschool, but the same materials are also significant and relevant in class 3, 4, 5, 6, 7, 8, 9, 10, 11, and beyond. Okay? It's a software that you put on that hardware, but we are always making things and joining things. And that's all that mathematics, or that's most of what mathematics is about. Okay? Let me conclude this by giving you, this was the easy part, showing you the most difficult part of mathematics in this language. Most of difficult mathematics is in what I'm just going to demonstrate to you. Okay, we saw that the area of a rectangle is like this. Okay, now what I've done here, I've taken the same rectangle and I've just skewed it. Okay, so what is the area of this shape? What shape is this? Something like a, this is a rectangle. This looks something like a staircase, yes. But if you want to put four sides to it, what a rhombus, not a rhombus because this side is not the same as this, a parallelogram. Okay. What I've done is I've taken this rectangle and I've skewed it to make a parallelogram. But the number of cubes is, the number of faces is the same. Yeah. So the area of this is the same as the area of this. Okay. Now I've taken the same rectangle, but I've skewed it differently. Okay. First I skewed it like this. Now I've skewed it like this. But the number of faces is the same. Yeah. So the area of this is also the same as that. Okay. So this area is the same as this area is the same as this area. Yeah. So the fact that the area of a rectangle does not change when you skew it, okay, most of difficult mathematics is just in that one. Okay, most of difficult mathematics, okay, later on we have measure theory, we have all kinds of very, abstruse, but most of it is basically this, because whenever you come to calculate something difficult in mathematics, in higher mathematics, you're calculating something called a determinant, usually. And this is what is a determinant, okay? Those of you who are in high school, okay, determinants basically tell you that when you skew a rectangle, the area of the parallelogram that is formed does not change, because things cancel out, etc. Okay? This is where the hard part of mathematics is. Okay, let's continue. So now, having quickly gone through most of mathematics with some examples, I think you might find what I say ahead as plausible. Okay? If everybody has to be comfortable with mathematics, can we conceive of a program in which all students will be liking mathematics, will be comfortable with mathematics on a national scale, okay? What do we mean by universalization of math? Every child should develop a liking for mathematics and a proficiency in mathematics. Okay, it should be the other way around. Next. And the key to every child learning mathematics is learning by understanding and only by understanding. Okay, next. And the pedagogy of this approach of learning by understanding is a two-step pedagogy. The first step is understanding a new concept in the familiar language of activity and things. Some examples we just did. One more example I want to do before, because I missed that. If this is my 1, now, what is this? Half, right? This is roughly half. And I can make 1/4 also, if I had more bottles. Yeah. And then I can join them, so I can add 1/4 and 1/2, Okay, I can make 1/3, I can do all kinds of things. So this is another very interesting way of understanding fractions, by making the fractions and joining them and seeing what happens. Okay, so it's not as if you need these cubes. Okay, it's not, the hardware is not so important. In fact, without any of this, just using this whole group here as a resource, we can do all these experiments. Okay, the hardware is variable. Hardware can be anything that is available. It's just how you put the software on that hardware, which makes things clear. So understanding a new concept in the familiar language of activity and things. Next, translating that understanding of math with things into the written language of numbers and symbols, which is the alphanumeric language of maths. Or numbers and symbols, what we wrote here, we call that, let's call that alphanumeric. But alphanumerics is not maths. Alphanumerics is just one of the languages of mathematics. Mathematics has many languages. Ultimately, you get familiar with alphanumerics, and once you do that, it opens up many avenues. Okay? But learning by doing and understanding is a universal method. It's a methodology not only for primary grades, it's also a methodology for upper primary and secondary math. And geometry and algebra can best be learned by this approach of making and measuring and understanding shapes. Next. You may ask the question, on what basis can we assert that something like this can happen on a mass scale? The lady in the picture here is the officer, education officer in Satara, in Kumte beat. She's the beat officer for a place called Kumte beat. Her name is Pratibha Bharade. And she has 40 schools in her beat. And she has taken the initiative to encourage all the teachers, okay, to help children learn in this by doing by activity. And all 40 schools in her beat are remarkable. Okay? So she has shown by example, by doing, that this is not something that can happen only with one gifted teacher. This is something that can happen on a mass scale. Okay? And now we have to think of a mass scale because after the Right to Education Act 2009, now the word good quality elementary education has entered law. So every child in this country between the ages of 6 and 14 is guaranteed by law a good education. And that includes obviously good math education. So what were the criteria of math education, good math education? Sawyer said enjoying math. Number 2, okay, confidence, thinking for oneself. Number 2. Number 3, some proficiency with the procedures. Okay, but enjoying math is basic. So if in a school children are not enjoying math, then clearly they are not getting a good math education. And that's why we need to do something about math education so that every child is enjoying mathematics. Okay? What we have to do, that is something which we have to discuss separately, but this is clearly what we are now mandated to do. Okay? And RT 2009 also notified the National Curriculum Framework 2005 as the curriculum for the whole country. And the National Curriculum Framework 2005, NCF 2005, has some very strong recommendations about quality. Okay. It has got a very interesting definition of quality. Let's look at that. It says that quality education is that kind of education which not only delivers equality of opportunity or equality of access. Quality education is that which delivers equality of outcomes. Okay, a much stronger definition. Next. So equality of opportunity is not enough. Good quality education must deliver equality of outcomes. And it further goes on to say, good quality education is defined as that which overcomes the inequality into which a child is born. Whether that inequality is due to economic factors, or gender, or social background. Okay? We can only say education is of good quality if the inequalities into which a child is born are overcome and the child enters, leaves school as an equal citizen. Next. So now, having talked about good quality math education, let's briefly talk about good quality science education. We could say that good quality science education is where all children are comfortable with science, all children learning science by understanding, and learning by doing and questioning, and developing scientific temper. Scientific temper, we'll see what that is a little later. Next. Now, to do experiments and learn all concepts through experiments, through trial and error, through discovery, school labs are there, but generally school labs are not used because if something breaks, then the teachers, or somebody is held responsible, so it's just there in the cupboard. But if the child has made the equipment herself and himself, then you're not afraid to use it, because if it breaks, you can make it again. So doing experiments with self-constructed equipment is a way to build up good quality science education. And in fact, a rural school has got a much richer environment than an elite urban school for learning science. So the real world is a powerful source of science learning, far more powerful than virtual reality. There's a lot of virtual reality stuff, okay, for learning science and learning mathematics, but real reality is a much more powerful than virtual reality. Virtual reality is supplementary, it's helpful, but not as powerful as real reality. And the real world is available in and around every school, hence universalizing the universe. We use the universe here as the real world in every school, every village, the sky, soil, water, plants, community. And rural government schools have a very rich environment. Next. So now we have to also talk about, because of RTE, not just being comfortable with mathematics, but being comfortable with science. And scientific temper is an important part of science education. Okay? Next. For universalizing the universe, apart from activity in the school, there are campaigns which happen from time to time. This year, in December 2019, on the 26th of December, there's going to be an annular eclipse, which is passing right through India, Karnataka, Tamil Nadu, parts of Kerala. And all of India will be having the partial eclipse. Okay? Such times are wonderful opportunities into which you can conduct mass campaigns using materials which are made by the students themselves in the school. Let me give you some examples of that. This is something known as a ball mirror. And if you were outside, I could demonstrate this to you. But if you use this ball mirror, which is just made with a plastic ball filled with sand and then an ordinary mirror which is pasted there, and you project the sun with this mirror, you get pretty good image of the sun, on which, if there are sunspots at 30 meters in a dark room, you can see sunspots. Okay? So this is actually a pretty good solar projector, a solar telescope. Okay? And this is a Dobsonian mount, a pretty good Dobsonian mount, but which can be made in every school. And we have used this in earlier campaigns in many Adivasi areas where the children have actually seen the eclipse using this. Okay? So they project it and they watch the whole eclipse like in real time on. Then there are experiments like the magic mirror, which is based on that, which is also a very interesting thing. I'm just showing you those. Children make this themselves. And of course, the solar filters with which you can ensure that lakhs of people observe the eclipse. And getting people to observe the eclipse in a country like India is important. Why? Very soon, just mention that. Next. That is because, unfortunately, today what we are seeing is what I call the mainstreaming of pseudoscience. And a very fresh example is what happened in the Indian Science Congress 2019, where we had a PhD Vice Chancellor of Andhra University who went there and gave a lecture to students, okay, and in which he made a number of claims. It's all on YouTube, you can go and look at it, it's a 1-hour lecture. At 1 hour and 30 minutes into that whole YouTube, okay, he's talking about the why the properties of the Ganges, which make the water always pure, no matter what you throw into it. Okay, here you have the Vice Chancellor in chemistry, okay, of a university, in a lecture before students, telling students why Ganges water is pure, and some sophisticated arguments about bacteriophages being present in the Ganges water, which purify the Ganges water. Now, when you have, this is not the first example, this has been going on since earlier also. Every science congress there's something like this. So it's clearly not something that is just accidental. We have to take it more seriously. And I would say that when you have a person like Nageshwar Rao coming and talking about Ganges water being pure, that's asking for it. And there's no reason why we should be stingy in responding. Okay. And so I'd like to propose, and this is probably what we're going to now do as a movement. We are going to now, I'm taking the same props which we have here. This is not Ganges water, but imagine that it is. Okay, and this is water which is out of your filter at home. Okay, and you're very thirsty. So you go now before children in schools all over the country with this experiment. Now this time they actually get the real stuff. Okay, I was thinking of sending, Nageshwar Rao a 20-liter bottle of Ganges water and asking him to, not drink anything over a few days, but just that stuff. But then I thought, if something happens to him, then will I be culpable of some, of some crime? So then, anyway, but we can go before children, and we have here a bottle of, imagine, this is a bottle of Ganges water, and this is a bottle of your home water, which is, and you're very thirsty. Okay, so which water will you drink? Ganges water?
No way.
Yeah? You have confidence?
If you don't know what type of water it is, you will be like, that's a full water, I like that.
Yeah, but if you know, okay, if you're told that this is water and you do some homework and you know what is there in not just the Ganges water, but the water of the Yamuna or the water of the Narmada, or water of all our rivers, then which water will you drink? This, right? And there are numbers. You can put numbers into this. Okay, like one of the numbers that is there already about Ganges water is that around between 11 and 12% of the serious medical problems in Uttar Pradesh are because of drinking Ganges water. And Uttar Pradesh is a very large state with very many crores of people, and 11 and 12% of crores of people is a very large number. Okay, so clearly there is a need to respond to this kind of, pseudoscience, and that's what we have to do with good science education, good mathematics education. So how do we go forward? Next. So our response is with a movement for scientific temper. And last year was the first year in which all over the country, the National Scientific Temper Day was observed on the 20th of August. 20th of August being chosen because it is the anniversary of the martyrdom of Dr. Narendra Dabholkar. And Dr. Narendra Dabholkar has probably given the best lectures, okay, in any language on scientific temper. I have translated 2 of them into English. They are in Marathi. But his lectures have now been translated into probably like more than 10 Indian languages as part of these commemorations. Next. And what we point out there is that you don't have to go to pseudoscience to talk about the scientific heritage of India. In fact, most of our thinkers have articulated rationality and rational thinking. This is from Gautam Buddha. Do not believe in anything simply because you have heard it. Do not believe in anything simply because it is spoken and rumored by many. Do not believe in anything simply because it is found written in your religious books. Do not believe in anything merely on the authority of your teachers and elders. Do not believe in traditions because they have been handed down for many generations. But after observation and analysis, when you find that anything agrees with reason and is conducive to the good and benefit of one and all, then accept it and live up to it. Okay? 2,500 years back, Gautam Buddha has written this. Some more things. Swami Vivekananda, last century before last, 19th century, he says, astrology and all these mystical things are generally signs of a weak mind. Therefore, as soon as they are becoming prominent in our minds, we should see a physician, take good food and rest. Okay? Superstition is our great enemy, but bigotry is worse. And the last one, to believe blindly is to degenerate the human soul. Be an atheist if you want, but do not believe in anything unquestioningly. So the tradition of asking questions of rational thinking is there throughout our history. Next. Gandhiji, whose death anniversary we will observe in a few days, he says he also emphasizes the importance of reason. And he says nothing in the Shastras which is capable of being reasoned can stand if it is in conflict with reason. Faith becomes lame when it ventures into matters pertaining to reason. So it's not as if you should not have faith. That's not what he's saying. But he says that when there is something, there's overlap, there's something which is amenable to reason, then we rely on reason. Okay? Next. And of course we have Jawaharlal Nehru, who first articulated the concept of scientific temper in 1946. This is what he said: what is needed is a scientific approach, the adventurous and yet critical temper of science, the search for truth and new knowledge, the refusal to accept anything without testing and trial, the capacity to change previous conclusions in the face of new evidence, the reliance on observed fact and not preconceived theory, the hard discipline of mind. All this is necessary, not merely for the application of science, but for life itself and the solution of its many problems. Now, understanding mathematics and a training in reasoning which one gets in the course of understanding and learning mathematics is something which certainly by itself it will not lead to scientific temper, but it is something which is conducive. It prepares the ground for scientific temper. The same for good science education. Next. And we have Bhagat Singh, who says, if after rigorous reasoning one is led to believe in any theory of philosophy, his faith is appreciated. His reasoning may be mistaken or even fallacious, but there is a chance that he will be corrected because reason is the guiding principle of his life. But belief, I would say blind belief, is disastrous. It deprives a man of his understanding power and makes him reactionary. Any person who claims to be a realist has to challenge the truth of all beliefs. If faith cannot withstand the onslaught of reason, it collapses. So across the spectrum, okay, and I've just given you a few examples, but in every culture, in every language, there is a rich tradition of rational thinking, and it's not from science only, it is also there in our democratic religious traditions. This is a point that I would like to make here. Next. But scientific temper is fundamentally against fundamentalism. By fundamentalism, we mean that there's a truth which is expressed in some holy document which cannot be questioned. And since scientific temper is based on questioning, mathematics is based on questioning, So anything that questions is incompatible with fundamentalism. So in that sense, our democratic religious traditions also are incompatible with fundamentalist trends in so-called religion, okay? Let's go back, just wait. And just go back, please. Yeah. So science which is based on questioning needs democracy. You cannot have science without democracy because you have to have the right to question. But at the same time, we know that questioning is also necessary for democracy. Next slide. So there is a very strong correlation between science and democracy. Okay? The scientific process is a democratic process. Everyone has the right and the duty to question. Science needs democracy. Conversely, scientific temper in society strengthens democracy. We have to respond to the attacks on democracy by resisting and expanding the democratic spaces as citizens and scientists. So when we go to schools, when we encourage scientific thinking, questioning, rigorous thinking on a large scale, on a mass scale, we are in fact preparing a foundation, strengthening the foundation for democracy. And that is the sense in which all of us as citizens, are enjoined to doing this. Next. And of course, this cannot happen by individuals. Everything that I've talked about here today is not the work of an individual. In fact, there is a large team of people who are working, who are doing this work. Some of them are sitting here. There's Dr. Nandu Jadhav of Navnimriti Equality, Sugandhi Francis, Geeta, Mahashabde, Atul Mahashabde, who are part of Navnimriti Learning Foundation. And many of you are part of organizations who are doing this kind of work. There is a movement which is going on in our country called the People Science Movement. And that's active in most states. And probably by the end of next year, it will be active in all states of India. So the PSM is part of the larger democratic movement in our country. And therefore, PSM, workers' organizations, farmers' organizations, women, youth, students, all of us have to work together to strengthen democracy. Because thinking for oneself, asking questions, is what democracy is all about. Next. So there are going to be mass science campaigns. There's going to be one in this year, 2019, around the eclipse. There's going to be one prior to that, the NSTD campaign 2019, National Scientific Temper Day. And I would like to invite everybody here to be part of that campaign in whatever way. If you're associated with schools or whatever, this is something which can happen and will happen on a very large scale. Okay. Next. There's going to be a March for Science 2019, which will happen around April probably. And I would like to invite everybody here to be part of that March for Science. This is what happened last year. And it was a very interesting event in which lots of people from all kinds of walks of society participated. Next. So if there is an effort to mainstream pseudoscience, there can also be an effort to mainstream scientific temper. And there can be plan A and plan B. Plan A is what happens if the government is participating and supporting. But even if it is not, plan B can always happen, can always go on. That is something which is happening right now. And that is needed clearly all over the world, not just in India, but also in Pakistan. It is needed in Afghanistan. Okay. It is needed in Saudi Arabia. It is needed in Turkey, in the United States of America, and even in China. Okay. If everything that I've said earlier is relevant, then clearly it is needed in every country. Okay. Wherever there are trends which are resisting questioning, that is something we have to strengthen this movement, and this is something which strengthens those democratic trends. Next. And unlike other countries, here in India, we have a very, very strong foundation, which is our constitution. Because probably the Indian constitution is the only constitution in the world which has scientific temper explicitly written into the constitution. So we are really doing what we have to do as Indian citizens when we encourage the aspects of thinking which make up scientific thinking and acting, which make up scientific temper. So with these thoughts, I'll conclude here. Sorry, I think I've gone a little beyond the time. If I have, please excuse me. Thank you very much for listening, and please feel free to not only ask questions, but even share your ideas on this. Thank you. Thank you, Arnab, for...
No, let's see if the audience probably has questions, and are there any more things for the kids to play with, or
No, I think that's...
You've demonstrated all of the things.
Right. Yeah.
Okay, questions for...
So my kid is just 4 years old, so to make him learn multiplication or tables, is this cube feasible, or like what is like, how to teach them tables? Because till the 10, 12 tables they will learn easily, like just rectifying and doing it, but then ahead tables which are like 31, 32 or whatever, like about 20.
Well,
teach tables about 20? I thought they stopped. I don't
see,
now they teach till 12.
probably teaching a kid you said he's 4 years old. A kid who's 4 years old, who's not yet in school, okay, in preschool, teaching a kid tables of that level is probably one of the things that we should not do, because
I'm asking if he's just 4 years old, but teaching him multiplication later age, what is the best way of teaching?
Well, at 4, I would not also recommend teaching multiplication, because if we try to do things too early or too fast, okay, then that sometimes ends up in the child not liking the subject. Okay, so liking the subject has to be the non-negotiable. Okay, so you teach whatever it is that the child is interested in learning at that point in time, and there is many things which have to be done before learning tables and before learning multiplication. Okay, so what are those things? Probably if the child is doing that, that is more important, and that will help the child do better in mathematics later, because those basic things are then built up in her mind. Okay, so my response to that question is, don't be in a hurry.
I just want that later stage.
At that class level.
Beg your pardon?
At that class level, how do you teach tables? That is
Yeah, that is my main.
Okay, so tables are usually taught beginning in class 3 and then in class 4. Okay, at that time a child is already 9, 8 or 9, okay, or even older. And probably the best way to teach a child tables is not to memorize the tables, but how to forget the tables. Okay, that's probably the best way to teach a child tables, how to forget the multiplication tables, because you don't need to memorize. Okay, when you need a multiplication, you should be able to do it very quickly without having to memorize, without loading your mind with all those things. Okay, now how to forget the multiplication tables? There's a well-defined procedure of activities which can be done. So maybe sometime when we do a workshop, on multiplication, if you leave your number with, then we'll invite you for that, and let's learn how to forget the multiplication table. Yeah. Right.
My question is, I really appreciate the reasoning part that yes, pointed that out, right? So, as far as I saw the whole presentation, right, so I felt finally one of the firm belief or the axiomatic statements, for the reasoning to come, right? But the axiom statements that were made was based on Indian constitution and also the education system that we currently believe in, right? And also, you're inviting everyone to see alternate methods to basically educate science, educate math, right? So I somehow feel that we should also question the education system by itself, right? Like, how do you see
Well, I am fully with you about the need to question everything, okay, and in particular to question the education system. Now, probably the best way to change the educational system is to show in practice that alternatives are possible. Okay? And if in practice we demonstrate that in one school or in 40 schools, okay, this is possible, then the whole space opens up. Because one of the strongest obstacles to educational reform and one of the strongest obstacles to, for example, mathematics education is that the belief that actually mathematics is not for everybody. Everybody cannot learn mathematics. Mathematics is for those special few who are good at mathematics. Okay, that's a very common belief. Now, if we can show in practice that everybody is learning mathematics and everybody is enjoying mathematics, then that falls through. So it is in these alternative practices that are your strongest arguments for educational reform. I mentioned Pratibha Barade and her 40 schools in Kumte Beat in Satara district. But here in Mumbai, you can go to, for example, the school at Kharghar of Vishwajot School. In Vishwajot School, I am informed, okay, I have not gone there myself interacted with the students, but I am told that all the students in class 9 and 10 enjoy mathematics. Now that's important. If children in class 9 and 10, all of them are enjoying mathematics, then that's something which is worth looking into. But you can go to a very elite school here, I won't take any names, and just ask the children whether they like mathematics. And I know there are many very elite schools in which children don't like mathematics. So enjoying mathematics, liking mathematics is something which is the alternatives that we have to show in practice. And by doing that, maybe we can bring about educational reform. Yeah.
My daughter is in 9th now, and the way you showed the graph, from 4th standard onwards, she started sliding down. And once I asked her, and she started doing very badly, I asked her, what is your benchmate doing, how is he? She said, he's very good in maths, but I'm very good in literature. And she said, literature is creative, maths is not creative, because you just have the formula. So when you show the early slides that, you discover and you become creative, that is exactly what is missing. So she was proud of herself not doing maths well because she said there is no creativity in maths. Luckily now she has found another person who is introducing that spirit in her. But I only hope that she has not missed the bus coming to 9th, struggling all the way.
Just a comment.
So I have a question. When you showed one of the blocks as one, and then you said, what if the small block is not one, but the 4 block is one? So I've met people who get confused with that concept of one, actually. One is a whole, other one is a one. How do you deal with that?
See, as I mentioned in the beginning, this was a 1-hour presentation of something that normally takes 3 days. Okay, so going from that one to the others is an activity which itself may take an hour and a half. And at the end of that, children are familiar with different ones. So through a process of discovery. Please. Yeah.
See, the blocks are also a bit abstract. If you give them a chocolate which has 4 pieces and call that as your one chocolate, then easily everyone can figure out what is half chocolate and what is a quarter chocolate. So use chocolates, chicky. We use a lot of chicky mathematics for fractions.
It's certainly one way to get things on your side, right? Also. That's awesome.
you might find difficulty convincing somebody who has gone to bad times to come in to be, subjected to mathematics. But if you can convince her, then there's no age limit. And that's something which you can start enjoying at all ages. But unfortunately, the older you get, the more, resistance there is, because it's based on their own experience, unfortunately.
If I may ask a question, this connects to your question about multiplication tables and chocolate. Do kids actually with no, preschool have an intuitive idea of numbers and, because at least I have seen smaller kids are very good in, when sweets need to be divided or something, they are very good with their mathematics. Without ever having been formally taught that. So, do we have a intuitive sense of numbers within us?
Definitely. Kids know what's bigger and what's smaller, which is more, which is less. And that's where maths comes from. And the kids enjoy shapes also. They like drawing, they like making stuff. They like breaking stuff that you have made, So all these things are mathematical operations. I guess the important thing is to keep it at play. Okay, keep it at play, and not be in a hurry to make it, that this is what you have to do. Keep it at play, exploration. Later on, that will happen.
Even music and beats.
Absolutely.
Symmetry in nature.
Absolutely.
All
Yeah.
these things are inherently mathematical, and I think we have an inherent, understanding of this concept.
That's right. Rhythm, music, dance.
I have a question related to competitive exams. Like, I used to give a lot of exams, MBA exams, and there are these, whenever you go for jobs, there are, nowadays there are competitive exams, competitive tests for that. So they test your proficiency in maths, like those MBA type exams. So where there are literature, this analytical, this thing test and maths test and something, and there the time limit is there. So if you are not able to do that much in that time, like you are then not qualified for that, and or you get this many wrong, you get this many right, and all that. You do wrong, there's some your marks get cut, something like that. Throughout, I'm talking in a very general sense. Like, so now is that procedure right, or is it like what can be the good thing to know? Because that should be based on certain talents. Talents of different kinds, probably. So the admission to a company or admission to a college or something like that. So nobody should be denied, probably based on, he doesn't know maths, or he can't do maths fast, or he doesn't know literature. So what is your take on that?
See, if I were hiring somebody for a job, I would look for the kind of skills that the person would need in performing that job or that responsibility well. And that's not necessarily being able to do mathematical calculations very fast. Okay? But making right decisions in the kind of circumstances that that person is going to find herself in. Okay, thinking for herself. I guess it would make very little difference to an organization if that person arrived at a conclusion in 2 minutes instead of arriving at that conclusion in 1 minute. Very rarely do you have to, take a decision which is, on the spot, Most of the time you have to take a right decision after careful thought. So arriving at a right decision by careful thought, knowing what decision is not a right decision, not jumping to conclusions, okay, these are the things, skills which are much richer. And it is this what, I've seen so many people who have done very well in examinations. Okay, they've done very well in examinations, but in fact they have not understood the subject. And it's very easy to, find out whether or not somebody has understood the subject. I, as a trade unionist, okay, I interact with all kinds of managements. These are people at the top. Okay, they are functioning there very competently. Okay, but they are not necessarily good at math.
I think there's a separate concept that he's talking
Yeah.
about.
Could you use the mic, please?
I'm sorry. So basically, a lot of these exams.
Let me just finish. But what they're good at is the kind of skills that their responsibility requires, and that's what is important. Okay, so being good at math, doing things very fast is not the essence of mathematics. What Sawyer talks about, who's a mathematician? A mathematician is a person who can think for himself, for herself. That is what.
Actually, when I asked I asked in that particular company why is this so? I mean, what is this thing? Obviously the HR wasn't able to answer. Why is this? Because this is something else, and this is something you're asking me to do, which is this will
absolutely.
take actually 40 minutes and not 12 minutes.
Yeah.
And if a person is good at maths, probably 15-20 minutes. So, probably what my guess is and what I have probably heard from people, they say they need to, reject some people.
They need to exclude, yeah.
Exactly.
Yeah, please say what you have to say. I think this is something that you wanted to say. Yeah, please make your point.
Some of these tests are really meant to exclude. Another aspect, which is what, when I was teaching my son and he's talking about is, the more you practice, certain aspects of what you practice become automated. So that leaves your mind a little more free to focus on more complex thinking. So certain basics with regular practice, you are able to automate that part of it, so that when something new comes along, you can focus on not on trying to understand what is this and what is that. Yeah. So there are two levels of so that practice is really essential to move forward progressively in order to take on more complex thinking, because the basics are already mastered. So it's a question of mastery. So there are two aspects to it. Like what you said, if it's 12 minutes, it's ridiculous. It's meant to exclude. But another thing is they want to test your mastery. Now, and what I've also noticed is when kids, the more they practice, the more they master, the more they like it. So it's almost like a circle in itself. Sometimes they don't like it, but as they practice and they learn to master it, they learn to like it. So there are many ways in which one can approach it, but I certainly do advocate consistent practice as a methodology.
See, I feel there are two things. One is that our education system is still behind the world. Because nowadays, 21st century skills, if they see what they say is it should be creativity, critical thinking, and decision making. These are the things which are the most important skills in 21st century. Because fast calculations can now be done by computers and calculators, and human beings don't have to do it. But if our education system today is testing that, and if that decides whether that door is open for a child, then I agree with you that even underprivileged children should be able to master it and should be able to get through that door at least to what they want to do, because all entrance tests are still so many years behind. So they are looking for these skills. So for that we may have to do some thing, and like Dr. C.R. Ramanujan, C.R. is Ramanujan. He was saying that education is a machine which we have to repair while it is running. So these things keep on happening, and we have
unquestioning acceptance of anything, and not willing to listen to an alternate point of view. That's to begin with, but to go further, fundamentalism today is actually the foundation of a lot of hate politics. Okay, and hate politics is something which is a problem in many countries, including our own country. So, the use of religion for hate politics is based on fundamentalism in many places, not just India, but India certainly. And when you encourage questioning, when you allow questioning, that is democratic. So fundamentalism is not democratic. Fundamentalism, in fact, tries to restrict democracy.
Can I ask you a question that has always bothered me?
Yeah.
So does it mean that if you're a scientist, you'll never be a fundamentalist about science?
See, what do you mean by science is, I think, a question that I would ask. What do we mean by science? There's one view of science which is science as a subject. Okay. There's another view of science which is of science as a way of thinking, a method. Okay. Now, if we understand science as a method, okay, a method of understanding whatever subject you are studying, then I would say that the world breaks up into two areas. Those which you look at with the method of science, and those which you choose not to look at with the method of science. The only thing that I would insist upon is that if you are claiming that something is scientific, if anybody is claiming that something is scientific, then that person should be willing to subject that claim to questioning. Okay? I would be perhaps fundamentalist about that one point, that if you are claiming something to be scientific, then that claim can only be made if you are willing to examine that area, keep it open to questioning. If you're not claiming that something is scientific and you want to believe in that, that's your democratic right also. I don't know whether that answers the question.
It does, I'm sorry, I'm pushing this because
Yeah.
because the other thing is that what kinds of questions do you engage with? And it's just because in any kind of practice, one has a history of process, right? A history of methods. But I think any kind of evolving practice needs also to be open to the possibility of other methods and other ways of questioning. And I sometimes struggle with maybe feeling that the doors, and this is not personal, I'm just saying in general in the field, that I sometimes struggle with the feeling that that if you're really committed to questioning, then what kinds of questions would you at least entertain? You don't have to agree. But how open is one, even within the scientific community, to actually entertain all manner of questions which may not make any sense to you at that point in time?
I think in science, if you're not open to questioning, then you're not being scientific. So, being open to questioning in a variety of ways, that is, I think, necessary in a scientific approach. Being open to questioning in various ways. Yeah.
I wonder, some of our scientists also are psychologists. So, science teaches us the rational thinking. How does
I agree with you, and that's because, in my opinion, because we often teach and learn science as a subject and not as a way of thinking. A scientist who is superstitious probably uses the method of science only in a very compartmentalized domain. And there's a large part of reality where she or he does not allow the entry of the questions of science. Whereas a person who is scientifically tempered, okay, scientifically tempered is a person who allows or who tries to use the questioning method and the method of evidence in any area that he or she is interacting with. So it is possible to pass and do well in the subjects of science without being scientifically tempered. And in fact, I would go further to say that very few scientists are scientifically tempered. Scientific temper is a broader concept, okay, and it means looking at the broader reality with the method of science. In fact, there is a resistance among many scientists to being too scientific temper. Yeah.
So I actually had a comment to your fundamental, I think fundamentalism need not go all the way to hate politics and, like things which are not good in intent. But fundamentalism can also mean, things which are maybe benign, which will not really affect you, but where again you do not have the option to question. For example, at home somebody tells you that you should not eat during an eclipse. Okay, classic one which I'm sure you've dealt with. Fine, the world is not going to change that if you don't eat for 2 hours or not. But the fact that you are supposed to take it on face value that don't eat during an eclipse, okay, is also a kind of fundamentalism which doesn't necessarily lead all the way to hate politics or something that disastrous on a larger scale. And that happens all the time because we have some preconceived notions which we are unwilling to let others question.
I know scientists, astrophysicists who do not eat during eclipses. So the question that I asked one such colleague is that your not eating during eclipses, is that based on a scientific analysis? He said, yes, there may be because of particular conjunction, there may be some kinds of rays which are reaching and which are. I said, do you really believe that as a physicist? And he thought about it and said, no, I don't. Then I said, would you, not eating during the eclipse, would you include that as one of your scientific beliefs? And he said, no, but still I would not eat during the eclipse. I would not eat during an eclipse. I said, that's fine. As long as you're not claiming that it is based on science, I have no problem with your not eating during an eclipse. The moment you start claiming that it is based on science, then of course we have to engage in a scientific discussion about that.
Any further questions? Thank you.
I would like to thank Junoon for giving me this opportunity to meet all of you here. You're doing some very good work, and this bringing together of the arts and the sciences, okay, is something which science really needs, mathematics really needs. So please keep it up. Thank you.
Thank you. And
Yeah.
thank you so